Okay, so let's begin. So it's a real pleasure to have Professor Laura Waller from UC Berkeley joining us here today. Professor Waller has been one of the key thought leaders in computational imaging and computational microscopy over the last 10, 15 years. She has done work in a whole variety of topics, from transport of intensity to Fourier tachography to the invention of the diffuser cam that she's very well known for, as well as many other topics, and more recently in the joint optimization of optical and computational imaging systems. She received her PhD at 2010 from MIT. She was a lecturer and a postdoc at Princeton for a couple of years before joining Berkeley. And so he's been there for the last, I guess, 15 years. She has a long list of awards. I'll just name a few. She just recently received the Max Planck Humboldt Medal, the OSA Adolf Long Medal for important contributions to the advancements of computational microscopy. That's presented basically to an individual who has made noteworthy contributions to optics at an early career stage. She is a Packard Fellow. She has received an NSF Career Award. She's a Moore Investigator. And she has received the Carl D. Salk Distinguished Graduate Student Mentorship Award. She is very well known in the field, one of the most well-known researchers in this area, and it's great to have her here. So please join me. Welcome, Laura.
I also grew up in Kingston, so I'm always happy to
course.
be in Ontario. I see none of my relatives who are threatening to come and heckle me, so good news for me. All right, so I'm going to talk about this diffuser cam project and all of its side pieces and some extensions that we're getting towards. It's all in this realm of lensless imaging. So I think a lot of people here know computational imaging. You guys have such great people here now with computational imaging, which is awesome. But I'll give you, start from the beginning. My definition of computational imaging is this joint, it's like a design philosophy, joint design of optical hardware and software, algorithms, machine learning. And it's this back and forth between the hardware and the software. So you need people who know both, who can figure out how to holistically design amongst the two, or even doing, nowadays, there's a lot of data-driven design where we're actually using the machine learning or optimization to not just get a good reconstruction out of the data that we've collected, but to decide what data we should be collecting, which I think is a really exciting area. So lensless imaging is a canonical example of computational imaging, because it's this idea of having a imaging system nominally without a lens. Sometimes there is a lens, but we still call it lensless imaging. But you have, for example, you take your camera, just remove the lens and point the sensor at the world. You take a picture, it looks like total garbage, but the light that hits the sensor might be the same light that would have hit the sensor if you had the lens there. And the lens's only job is to bend the light rays in a particular way. So if you could imagine, if I can digitally bend those light rays, I could potentially reconstruct the scene from the same light. Right? No? Maybe. In practice, this inverse problem is too ill-posed. Diffuser cam is the idea that if we put just a bumpy piece of plastic, like a diffuser, you could use Scotch tape. We started the whole project with the privacy glass stickers, the stickers you put on your windows so your neighbors can't see in. You just put that on top of the cover glass of the sensor and take a picture that looks like garbage, but now it's structured garbage and I can reconstruct a nice image from it. Some people in optics might recognize the Thor Labs dog. Or Grace, who's now at Meta Reality Labs, putting diffuser-like phase surfaces into the new Oculus. So these kinds of cameras are computational imagers. They're very different than regular cameras. So think about a regular camera. You have some scene in the world, and you have a lens that focuses a point from the scene onto the sensor. And the idea is that your sensor then captures exactly what was out there in the world. Whereas diffuser cam is one of many mask-based lensless sensors, meaning you put a mask somewhere in front of the sensor, but close to the sensor, so everything could be compact. And close to the sensor also means you're going to have a large point spread function. So a point in the world doesn't map to a point on the sensor. You don't have this one-to-one mapping, which means your forward model is not just a delta function. It's this point spread function. So point spread function means point to the world, or what do you get on the sensor? And this one looks like the bottom of a swimming pool on a hot day. That's called caustics. And we just did this with like privacy glass sticker, and then we put some black tape to make it like sufficiently limited in size because it's simple and easier that way. You don't really have to do that. But you can literally make this with Scotch tape if you want. I had 2 awesome undergrads who built a tutorial on like how to pull the Scotch tape slowly enough so that you don't get it like stretching in one dimension, and some code that you can use. It's pretty fun to try on your own on the weekend, or if you have kids, you can try it. Okay, so some properties of this thing. So you have a point in the world and it maps to this pattern on the sensor. This is what I call multiplexing, because a point maps to a lot of pixels. Or conversely, if I have a scene out there, then since every point maps to a big spread of pixels, then every pixel actually measures information from a big spread of different points within the scene. So that's what multiplexing is in this context. If I move the point, what happens? It just shifts this pattern. So what does that mean about the system? Signals and systems people? It's shift invariant, right? And so if your system is shift invariant, it means I know the point spread function, like take the response of the system to one point, it's the impulse function. Then if you know it's shift invariant, then shifting the point means you just shift your response. And so you don't need to measure an individual response for every point in the scene. If I light up 2 points at once, I get the linear sum of the intensities that either one creates. If these were if this was a single laser, you'd get interference patterns, and this wouldn't be true. But because our points in this case are assumed to be mutually incoherent in some way, then it's just a linear sum, but that means it's all a linear system. I can write it in matrix math where I have like my scene. If I just raster scan my scene out to X and my measurement, then I can talk about A being this like forward model, or like the operator of the system matrix. And optical design has spent centuries trying to make these A matrices as close as possible to the identity function, because then your scene gets directly mapped to your measurement and you don't have to do any inverse problem computation, right? Computational imaging just throws that all away and says that what matters are the properties of A, that as long as it's known and invertible, A can be anything. And I'm free to choose A to be something that allows my hardware to be cheaper, simpler, smaller, or whatever else you're looking for. So like you need to know this A matrix. And that's not obvious, right? Like, so what can I do to like know the forward model? You could go and like put a point in the scene and measure every like the response for every point in the scene. And basically you can that would map out this forward model column by column. You could do that, but if you're talking about a 1 megapixel image, you're talking about 1 million calibration measurements, and then you need to invert this million squared base tricks, which is insane. And that's only for 1 megapixel, and we want to do much more than 1 megapixel. So you could model it. If you knew the surface shape of this diffuser random bumpy pattern, then you could model how light propagates through it and figure out the responses to the system. That's also infeasible because like you don't have any of them at home, and we want you to be able to build this at home with your kids. That seems to be our main goal. We could machine learn it if you give enough input-output pairs, but then you need training data. So I'm going to show you some like combination of all of these. But the main idea is this shift invariance, that as you shift a point laterally, the point spread function shifts laterally. And what does that mean about that A matrix? Any matrix math for you people around here? It's shift invariant. It's circulant. Yeah, it's circulant. So this A matrix is fully determined by a single column because it's a convolution. So a convolution matrix, you don't need to measure the whole thing. In fact, we never talk about convolution matrices because we don't do it. We don't even instantiate this convolution matrix because every column is the same as the previous one, just shifted in a particular way. So in our particular case, this point spread function shifts around in 2D. This is really only showing you 1D, but it does shift off the edge of the sensor. So there's a cropping that also happens, which I'm just going to completely ignore, but trust that we deal with it properly in our algorithms. And yes, we don't instantiate this matrix because it's wasteful. We just do a deconvolution in Fourier space. So you go to Fourier space and it's just a divide one matrix by the other. So it's basically two Fourier transforms instead of a gigantic matrix inverse. And that's because it's shift invariant. So we want to design our optics to be shift invariant. And that wasn't an accident that they are shift invariant. So here's some more pictures. This is the raw data for Grace and her dog. Here's a much prettier picture. And then I want to talk briefly about our algorithm. This is pretty outdated by now, but this was like, it's a long time ago now. This is the algorithm we use. We're just having like some data consistency term, minimize the difference between the measurement and the expected measurement given your forward model, which is just a convolution with this measured point spread function. So we measure the point spread function ahead of time, take your iPhone flashlight and go far away and turn it on as a point source. And then we have several constraints. So the first constraint is that you can't have negative intensities. That's just physics. You can't have negative intensity light, energy. And then this is like our regularizer term, which is flexible, and we do different things. Most of what you're seeing is going to be a total variation, regularization, and it's not an ill-posed problem, so we don't rely on it too much. But later I'm going to get into compressed sensing, where the regularizer becomes absolutely critical to even getting an answer. Okay, so I mentioned this is old. You can do this, like I call this the physics-based or model-based reconstruction using iterative optimization. This was ADMM. But of course, you could like try to be cool and make a machine learning network to learn all of that input-output. It's a convolution with a humongous kernel, so like CNNs don't work great, but you can do various different tricks. And we did this like to compare. So we thought a lot about this sort of spectrum between physics-based, like iterative optimization techniques, and then like deep learning based. This is also getting old now, but there's a lot, like sort of from the high level, there's a lot of different trade-offs in terms of interpretability and speed. So the deep learning seems to always win on speed, but it has issues of not being interpretable, and you need training data sets. But it can also find some really interesting like fixes to artifacts that that might pop up in the model base because you're not modeling everything. So if you don't model aberrations, or if you don't model something else, then they will turn up as model mismatch artifacts. But the real play is to see if you can figure out how to use the best of both worlds. So use the physics you know and learn the stuff you don't know. So we did this by unrolling the ADMM and then learning the hyperparameters for that. And what you can see here is in this case, our physics-based solution is slow and bad. Our deep learning is fast and bad. And our sort of like putting them both together in the smartest way we could think is fast enough to be real time and slightly less bad than the other cases. And I think this is a nice example where machine learning and physics can work together instead of competing. And I really do believe in this idea of like using what you know. And I should say like this used a lot less training data than we needed for the like full deep learning case. So you can get away with, you basically have a much more efficient neural network architecture because the architecture is constrained by the physics. All right, so like there's still artifacts, right? Another approach we went to trying to solve these artifacts. We did a lot of these in time, different orders, so it's trying to tell the story to make sense, but this was like back when we still had like lower quality to start with. But Tiffany was working on, we do a lot of stuff right now in space-time methods, so trying to use like video data to reconstruct better images. This works better if you're doing like multi-shot computational imaging, but this is single-shot computational imaging, but we can still take advantage of space-time redundancies or like low-rank behavior in space-time if we have a video from this diffuser cam. So the like space-time method that has worked best thus far is this this like simple representation using multi-layer perceptrons where like we have two. One is to represent the motion and one is to represent the scene. And represent the motion basically means we're trying to represent the scene, and we're saying that over time, the scene is just warping. Like you'll have like local direction vectors of where things are going. And we're trying to solve for that with the motion MLP. And then the scene MLP is trying to solve for the static scene at a given reference time frame. And this has lots of caveats, but it does seem to clean up our videos quite nicely. This is some pretty low quality data to start with. Here's another example. also has lots of issues, but you can see that the space-time neural network does do better at least. Okay, so with that and showing like obvious artifacts, I like to get to the like cute, but what's it good for? It's like, yeah, you can make your camera smaller, you can make it thinner. You could make your iPhone camera thinner, and it would be useful to make it not take up as much volume in the camera. Could you make it cheaper? Not really. They're already using like printed plastic optics. That's dirt cheap if you do it at scale. So, so probably not going to win on that dimension. But you have to suffer from all these artifacts and a lot more compute to get it to work. So, like, I do believe that with enough development, you could make a cell phone camera using this technology that would be thinner and as good of quality. But I didn't want to take that risk. I don't want to be that person trying to sell that to Apple, because I don't believe that we're going to easily get to like the kind of qualities you're getting with actual lenses. And so like we started trying to think of like, what can this thing do that regular cameras cannot do? And one of the first things we looked at was this big PSF, this multiplexing idea. And if you have a point that's like off the edge of the sensor, so the point is centered here, but because the point spread function is so large, you capture a little corner of it on the sensor. So you're capturing information about points that are outside the field of view of the system. And so we were like, cool, we can try to solve for what's outside the field of view of the system. A regular camera certainly cannot do that, right? So we tried that and it didn't work very well. It looks like pretty good right here and like pretty close to the edge. This is our like original field of view. And like it's okay close to the edges, but like outside here, you're just not getting enough information. And now this is compressed sensing. You're trying to solve for more things than you measured. You're trying to solve for a bigger field of view. Okay, so we gave up on that. It does work much better if you have like a measurement and you just cut out a central chunk of it and then try to fill it in. So like interpolating rather than extrapolating. That works much better. Or even better, you can throw away 90% of the pixel information in the measurement if you randomly choose which pixels are non-zero. That works very well, but like nobody has there's no reason to throw away all your pixels on your sensor, and there's no sensors made with random located pixels, and it'd be very expensive to do so. So, okay, so then the only like sort of real world case we could find for this was like, what if I'm trying to do an array of sensors? So there's reasons why we don't have a like 500 megapixel sensor available. Like there's circuitry reasons for that. So you can get like a bunch of sensors, say a 2x2 array of sensors, say each one is a couple megapixels, but you can't put them directly next to each other. They always have some like border around them for circuitry, which is important. And so you always have these like gaps between them. Like this is why you wouldn't make a sensor array for a regular camera. But now, as long as our point spread function is bigger than the gap between the sensors, we will multiplex information from all of these black areas into the sensor measurements. And then we have a chance to solve for like the whole thing, including the black spaces, from only measurements here, as long as compressed sensing wise, you have something low rank that, or like, you know, it's low rank in some basis set. And so natural images, like we're just using like TV here, but this works pretty well. So then like Kevin is a postdoc in my group. He just started his own group at University of Michigan actually. But he had this giant sensor array. It's like a credit card sized array of sensors, like 6x8 array of multi-megapixel sensors, 13 megapixels each. So, and they can run at like, you know, tens of frames per second. So you can get like 630 megapixels per frame, but then we're going to try to fill in all the gaps between it. So we're talking about like 3 gigapixel reconstructions in each single shot, and then try to run that at like the frame rate of the sensors. The fill factor is only 23%, but I already showed you I could do it with just 8%. So Kevin had this beast of a sensor, and so we wanted to play with it, so we did. Rajesh Menon from Utah made us this diffractive element to serve as the diffuser. So I haven't gotten to it yet, but diffuser is not the best possible point spread function to use. So this point spread function is just basically like a random array of dots, single points. We designed it as such. It's not necessarily the best, but it works well for this situation. And we were able to like fabricate it easily with Rajesh. So Kevin built all of this system up and was able to get, he did it as a microscope. So he also has a big lens in there to magnify things. And so he can get like very high resolution across a humongous field of view at pretty fast time rates because of this like multiplex sensor. Okay, yeah.
So I assume, I guess here you have to work in an orthographic regime because, like, what is perspective? Like, what would a perspective image be?
So okay, so no, you can deal with that, but he didn't deal with that against my will. He built a Fourier system and put the diffractive element in Fourier space, and so it is a telecentric system, but I didn't want it to be. I wanted it to be a giant diffuser cam, and he really only did it. He thought it would be simpler to do the microscopy to like zoom in because we were trying to look at a specific resolution, and the pixel size of the sensors is just set. It's very small. But then it caused all kinds of problems because this thing is credit card size. So we had to buy like old like mi-camera lenses to be able to make a Fourier system. And it's a horrible Fourier system. It's full of aberrations. So most of the work here was fixing all of the aberrations. And I firmly believe that if he had spent the time doing the lensless version, it would have been easier and quicker and possibly better. But he got a job and he left. So and this looks good. And he can do microscopy now at the exact resolution that he was aiming for. Okay, so the other direction that we were going in this, like we were doing these in parallel of like, what can we do that regular cameras cannot, is 3D. And if you think about a regular camera, you have a focus plane, and stuff that's in focus is sharp and clear, and stuff that is out of focus is blurred. And the blurring is like, you know, approximately a Gaussian blur for like incoherent scenes. And that is just like a Gaussian blur blob you cannot deconvolve nicely, right? So the idea is that things that are out of focus, high spatial frequencies are simply gone. Whereas with these lensless cameras, if we're dealing with like stuff out in the world, pretty far away, so now we're back in the lensless regime, so they're past the hyperfocal distance of the sensor, of the camera, then when you move things in 3D, then what happens, you just get a different response of the system. And here's just a simulation. I'm just moving my point source axially now. And what you see is basically it's the exact same caustic pattern for this particular design. This is a fairly smooth, it's not a super highly scattering, it's not a diffractive element. But now as I move axially, I'm seeing my pattern stay the same but scaling, which is super cool because now I can still remain with one single calibration measurement. I don't have to have like a precision motion stage to capture the PSF at different depths or different lateral positions. And I can predict the response of the system for all points in a volume. And the response of the system is different for each point in that volume. So I'm like in business for trying to reconstruct 3D. We're still going to try to stick to single shot. So now we have a single, like say it's a megapixel measurement, and we're going to try to solve for say like 100 depth planes. So now you can see I have a big problem. Well, if I was going around like individually putting in impulse functions into each position in X, I'd be in really big trouble because now I'm trying to solve for 100 million things. And then my forward model is just this like convolution, block convolution model where the point spread function is scaling at every different depth. So I end up with this like very underdetermined problem, but I've solved the calibration and computation problem by using this convolution model. But it's severely underdetermined. I'm trying to solve for, in this case, 100 times more depth planes than like pixels measured. So this is pretty highly leveraged compressed sensing. But our multiplex measurement is appropriate for that. So as long as your sample is sparse enough in a way that you can know, then you can do this. So here's like an example. This is the raw image we collected, single raw 2D image of this little leaf. And here's like the reconstruction, and I'm just like spinning it around so you can see the depth information there. One of our key technologies to apply this to was we work with neuroscientists on neural activity tracking. So you're trying to track which neurons are firing, which individual neurons are firing inside a living organism's brain. This is zebrafish, so it's easy, but we largely work with mice. There's not much to see with mice, but basically your neurons are a couple microns big, and you can do this like optogenetics-like trick where when the neuron fires, it lights up, it fluoresces with a particular wavelength. And so that's what we're watching here. Like these are individual neurons firing, and they're firing at like millisecond time scales. So that works well with the like tens of frames per second that you get with a regular sensor, but it has to be in 3D because these neurons are all organized in 3D. And so this was like a good technology for that. We would like to like head mount this on a mouse while they're like running around and behaving. We've kind of moved towards other technologies in the mouse for various different reasons, mostly optical scattering. And the Rice group has actually done something very much like that. So you can look at that stuff, but it's really interesting to think about. So yeah, so here's just another video from our Miniscope version. This is like a popular open source spectroscope that we hacked. You take this 2D video and you can make a 3D video. This is a water bear or tardigrade. They're so cute. They're like little caterpillars crawling around, and we're getting pretty good 3D. So in the microscopy case, you are always going to suffer in the axial dimension, have worse resolution than the lateral, which is sort of just a given. Okay, so I'm talking about using a 2D measurement to get 3D. It is compressed sensing. We're relying on sparsity, and so you have to make sure that will work. We actually have done this like a couple of different 3D, so XYZ, XY time, and XY lambda. You can ask me about those if you want to hear about those. Otherwise, I'm going to skip them because I want to get to the last part of my talk, which is in this realm of computational imaging is awesome, but I'm only halfway through my talk, more than halfway. And so I want to get into some of the dark secrets. And I think like one of my favorite quotes is like, NASA's like, triple redundancy, we can't afford to fail. And compressed sensing is like, look at all that redundancy, I can fix that. And so I really think like we have to consider this, like we're trying to make our imaging systems as efficient as possible. Every measurement I take is super important. So then every error I get can be super important. It propagates to like artifacts that can be quite bad if you have small errors. But that's just a trade-off you have to make if you want efficiency. So I think there's a lot of black magic in computational imaging that where like you get this one beautiful paper and then nobody can replicate it, even yourself if somebody sneezes. And so we've been thinking a lot around like how you can make these systems more robust, but also still remaining efficient. So there's definitely like you have to choose your way along this trade-off. But a couple of the dark secrets of this diffuser cam project. One is that this is not a telecentric system. It's like well, you guys are probably familiar with photography. So like the resolution changes a lot with depth. So this is like the resolvable buckets. Laterally, it just goes out, sprays out linearly, but axially goes off as 1/z. So I was saying like in photography, our hyperfocal distance is 2 meters, which means everything beyond that, we're not getting any axial resolution. So all that 3D stuff I showed you was like us placing stuff pretty close to the camera, where the resolution is closer to isotropic. And you cannot get like a few micron axial resolution at like a 10-meter standoff distance, like for self-driving cars or something. I've had lots of people ask that. And then our photography stuff is further away and it's not capable of doing good 3D. Another caveat or dark secret is that we started the project with these privacy glass stickers, or they're like, we call them Gaussian diffusers, or they're just like smooth diffusers that make these caustic patterns. The caustics are actually a pretty good point spread function because you still get, like if you look at the Fourier transform of this, it still has lots of spatial frequencies, high spatial frequency information in it, which is what you need to get the high resolution reconstructions. What's bad about them are that like these curved surfaces, like the concave surfaces are focusing light, which is good for SNR. Like Poisson noise wise, you want to pile the light into as few spots as possible. But then like the curve, when the curvature goes like the opposite curvature, then you're spraying the light out, and that's just bad. That's just contributing to like this like washout effect, which is really bad. It's also the washout effect is also why we don't look at objects that are like a big white wall, because it doesn't, that like hurts us a lot SNR wise. If you think about it, it's just the convolution of this PSF with your image. So neither of them should be just like a big white box. It's not going to work very well. Okay, so you can go to a regular camera and get a really nice focus spot. This is actually the best you can do SNR-wise. If you're designing an imaging system, if you don't care about compactness and you don't care about 3D, just a regular sharp PSF is the best you can do SNR-wise because it's Poisson noise. But then, like if you're doing 3D, then this like points per function blurs out very quickly as you go off focus, and so that like starts to be really difficult to deconvolve. Okay, so you could like go for like the light field approach and put in an array of spots that piles the light up into less spots on the sensor, but keeps you with this big point spread function that allows you to do the multiplexing. So all that compressed sensing doesn't work for a single spot like a regular lens. But then if you have a regular grid, then as you shift sideways, your point spread function shifts and you get to like, these two point spread functions are almost the same. You can hardly tell the difference. So you get these ambiguities, which are due to the periodicity of the point spread function. So then like we've come to randomly spaced microlenses, and this was like heuristically what we came to, but we've also done some like end-to-end stuff to verify that this is pretty much true, that now when you shift it, it's still gonna have uniqueness. So like I don't have a lot of results because all my diffuser camp people graduated after we got toward being able to make these arbitrary designed phase masks. But Layla has built some and shown like, this is our original diffuser cam PSF versus one of these. So this one's designed for 3D, so actually it's a random array of microlenses, but each one has a different focal length so that we can have sharp information at lots of different depths. But that's what we had, so she did the 2D version. It's already a lot better than the diffuser itself. Here's another example where we can see like significant improvement in the quality of the results as you change to this like random grid of spots PSF. Okay, so then another big dark secret is that I keep saying it's shift invariant and it's not. And basically, if I go far away, it is shift invariant. Because if I go far away and I use a diffuser that has relatively smooth bumps, so relatively smooth bumps mean that I'm going to have a smaller angular field of view. And then when I go far away, everything is really very shift invariant. So the shift invariance is related to the Fresnel approximation, which is like, is that diffuser thin, like optically thin? Like if you come in at very high angles on a diffuser, you actually see different things like in tomography. So like you can quantify this, but like privacy glass sticker, for example, does well out to like 40 degrees or so. And so like that's fine for photography. If you want to do microscopy, you're bringing the object right up here and you have to think about high angles. And then like, so all that microscopy stuff had a lot of problems because we're coming really close to the sensor, like same design, but we're coming really close to the sensor. We have to deal with high angles. So the sensor doesn't pick up light very well at high angles. It's not designed for that. That's one issue. We just sort of bottled that and dealt with it. But the bigger issue is that it becomes less and less shift invariant the higher and higher the angles you go. So if you come in like this close to a sensor that's like this big, then your angles are much larger than 40 degrees very easily, right? And so like here's an example for the microscope case of what the point spread function looks like. This is our random microlens array point spread functions at different points in the field of view. It's wildly different, right? This is not shift invariant. And so like our initial approaches were like, we'll just like do local convolution, local like shift variant. So like if you just pretend like it was shift invariant and use the center point spread function, it looks terrible. But if you like locally, if you like measure the point spread function in like a 3x3 grid, then you can largely fix it. And this worked well for these kinds of things. But it's also like, you need to be working in a place where you can measure accurately these different positions. We've since gone to like a lot more thinking about like these like physics-based versus deep learning-based approaches, and that's kind of like the physics-based approach. We've done this deep learning-based approach. I'm not really going to get into it, but I wanted to go more generally into thinking about space-varying aberrations. So I'll just really quickly get through this project. It's like slightly unrelated, but also related. And the idea is to think about doing a deconvolution. So our reconstruction is just a deconvolution, but now we are like releasing ourselves from diffuser cam, and it can be any imaging system. So any imaging system with aberrations gives you some aberrated image. And so you can try to reconstruct it, but it's not always going to work, right? So if you have a microscope, we often see that you have less aberrations in the center of the field of view, more aberrations at the outside. And then like if you just go and measure the point spread function at different points in the field of view. Now I'm talking about a microscope, so it'll be like you're trying to make a point and it'll just be like smooth variations to a point. But you run into this like calibration issue that you need millions of images to properly calibrate a fully shifting variance system. So Amit along the way came up with this idea that like most like traditional optical microscopes are rotationally invariant. And so you can basically do like, it's basically like polar coordinate deconvolution, and you assume rotational symmetry to get like, to reduce everything by a dimension. And that makes a humongous difference. So what you're saying is that the point spread function is going to be the same at every point along this given radius, but it's rotated at the appropriate angle. And so then if you want to calibrate the whole system, you just need to measure the point spread function along a line. But you don't even have to do that because you have 2D, so you can sort of like randomly spread a bunch of point sources throughout the field of view and figure out the rotationally varying aberrations with this assumption that it is like radially. So the aberrations are not radially symmetric, but the imaging system is. So we don't actually even solve for a whole line of aberrations. We just solve for the first 5 Seidel coefficients because that works. So most modern imaging systems don't need more than that. We actually tried more and it doesn't help much. So then you only really need like 5 point sources somewhere within the field of view, and that's very easy to achieve in a fluorescence microscope. You just spray some fluorescent beads all over the place. And then we go into this, we call this ring deconvolution. It's basically like polar deconvolution. And there's analytical theory that you can say like you can get exact deconvolution results, you know, exact if you have no noise, et cetera. But then you can like do an analytical solution to get to do your deconvolution similar to actual deconvolution. Or if you want it to be faster, you can do the deep neural network version. We used to call it SeidelNet, that solves for these Seidel coefficients and uses them to do the deconvolution. And it's much faster. We can't guarantee that it's going to give you the right answer, but it usually does. I'm not even showing both of them side by side here because they always look so similar. And this will help you with space varying aberrations if they're due to a rotationally invariant imaging system. So this was like a really nice example. Like in the real world, what you see in like microscopes, we actually had a hard time finding microscopes that have a lot of space varying aberrations because microscope designers simply crop the field of view until the aberrations aren't hurting them anymore. And so the idea, I think, with this is that you could potentially design your microscopes around knowing you can correct the edges of the field of view and make it bigger intentionally, because I think like our sensors have the space bandwidth product to handle that now. To find examples where it was actually useful, we had to go to miniature microscopy where you can't correct all of the aberrations, you don't have enough space. So these are from a miniature microscope, the mini scope. See, like at the edges of the field of view, you do much better here. So I'm gonna stop talking now, but this like deconvolution is just like computational only solution, which I don't like. That's not computational imaging in my books. We need to move to this space where we're messing with the hardware. So the fully optics solution is basically adaptive optics, where you correct all the aberrations physically, or like actually putting lens elements to correct them. The computational fully solution is deconvolution, and there's only so far you can get with that before you didn't measure the information. And this one is we're trying something crazy where we put a diffuser into the Fourier plane. It's not a diffuser, it's like a phase mask into the Fourier plane so that we mess with the PSF, but it keeps all of the high frequency information alive, and then we can do a better deconvolution with it. And I'm not going to have time to get into that. So I will stop now with my summary that computational imaging is awesome with a lot of problems that we can fix with computational imaging. And so thanks to my group, all our collaborators, my NTech collaborators for letting me leave for almost a whole week now. Happy to take questions.
Yes, so you mentioned some physics informed deep neural networks. How about the like I'm wondering what in practice, how about the implementation look like? Would you mainly adjust the loss function or the architecture or the data modeling? Yeah.
Yeah, I think I used to have slides on this. Yeah, so we took ADMM. And this is actually a while ago now. There's probably better ways to do this. We took ADMM and we unrolled it. So each layer of the neural network does an iteration of the ADMM.
Mm-hmm.
And then you can learn all of the hyperparameters for it. That's basically what we did originally. And it runs into lots of problems, like when we had to do 3D. You run out of memory for this, so you need to use like checkpointing and a couple of other like memory saving tricks. But that's basically what it amounts to. Yeah.
Well, I'm interested in the last part you mentioned.
I can talk about that.
But isn't I mean one of the issues with spatially varying stuff like aberrations is that they're not so easy to express in the Fourier domain. So
right. Yeah, so we've actually talked a lot about this. Space varying aberrations amount to like a 3D aberration function of the pupil, which is completely related to like imaging and scattering, and like the transmission matrix is basically that. Remember I said like don't go through it every point and make this giant matrix. That giant matrix is the transmission matrix. And people are doing it, so you can do it. It feels like not so elegant to me to like just measure everything. It seems like you should be able to do better. But if you have spatially varying, you have to do something. You need more information, so you have to do some more measurements. Not clear to me that the transmission matrix is the way to go, or that the transmission matrix can't be like sampled better, which I think like some people are coming out with more recently. But so like one thing to think about is like where does space varying aberration come from? It has to come from like if all of the aberration is happening in the pupil plane, then it has to be spatially invariant. And so like the reason you have spatially varying aberrations in real imaging systems is because you have optical elements off the pupil plane. Or like the aberrations in the lens can be mapped to the pupil plane, but if they're like in the pupil plane, they will only cause space varying aberrations, right? So like my approach would be to say like, where's it coming from? Is there like 3 layers of lens elements? Then you probably need to correct 3 layers, which means you'll need at least like 3 times as much data measured. And it's not exactly clear how to measure that, but I think like at least you can figure out like the data limitations of like what you should be able to get to. But you certainly, I don't think, should have to measure the whole thing. There's got to be some in between. Yeah.
Thanks for a great talk. Though. Very, very interesting. We were on a biophotonics lab with Francis Martin Hospital, so very interested in subsurface kind of depth imaging. So is there a diffusive element, metasurface, diffractive element that would be optimized for depth or 3-dimensional imaging?
It depends what your goals are. I mean, like,
we showed the zebrafish, but that's nice and transparent. So that's
yeah. So if you have like we have a whole other thread in our group of imaging through scattering, but it's largely coherent imaging. So like if you want to deal with 3D properly, I think like coherent imaging is a lot better. You have a single complex field that's passing.
Coherent imaging?
No, like diffraction tomography. It's related to OCT. So like using a laser and putting it through at different angles, for example, and then you could get 3D information by diffraction tomography.
To what depth is it?
Oh, it totally depends on what
like microns or tens of microns?
Hundreds of microns. Like we're trying to compete with like OCT can go deeper, but it depends. You always have this trade-off between resolution versus depth, right? And so it's very hard to give a number on it. But the idea is that if you can model multiple scattering through the sample, you can digitally do it. And so to model it, you have to figure out like what is the 3D refractive index of the sample. So that's a tomography problem that's sometimes solvable and sometimes not.
What if you just have a bulk measurement like scattering coefficient or something as opposed to refractive?
That's not going to help you with perfectly correcting all of the scattering to get back to diffraction limited, which is what we're after. But yeah, depending what you want to do, you could probably make trade-offs there.
Any other questions?
For the 3D part, when you compare it to like handcrafted things that people do, like rotating DSFs and things like that, how does the lenses configuration compare?
Yeah, it depends what you're doing. So I think first, all that stuff's been used in single molecule imaging, where SNR is the issue to deal with, and I don't think you should spread your photons across so many pixels for single molecule imaging. I think already the rotating PSFs already have problems with that, and that's been one of the criticisms of like some of these like end-to-end optimized versions, is that you have to know exactly what your SNR is to find the best and what your density is of your spots. So like I don't think this approach is good for that because of the SNR issues. Just a different regime, but it's similar. They're both just PSF engineering. Right. And if you think like almost, so like if you wanted to design, you could design a phase mask that sits fairly close to the sensor. If it has lots of high frequency information, you can move light to high angles and get a smaller PSF, which is like piling the light together more. That will help you with SNR. But if you're trying to get a relatively small point spread function, probably putting a Fourier space mask in a forest system makes more sense. But it depends, like if you want it to be compact, then you probably need a bigger PSF. Sometimes, and so like the big PSF helps you with compressed sensing, but it hurts you with SNR. So like choose your poison. Yeah.
Just wondering, what's like the axial resolution for the diffuser cam? And like what's the limit on the axial resolution?
It's just diffraction limited. So you have like, depending how far away your sample is, the size of your sensor sets the angle that gives you a numerical aperture. And it's just like n sine theta. So it's just diffraction limited. So there's nothing to win there.
Any other questions?
I'm curious about the equation of the PSF. If you like change the intensity or the wavelength of the your light source, and then you will get another PSF, right? And if the PSF is not accurate, it will affect the final construction result.
It'll just look like it's at a different depth.
So it's just a different depth.
Yeah, and actually, so we do a bunch of like color imaging, right? And we calibrate the PSF at each color, but it's less than a pixel difference, so then we just don't bother.
Oh, okay.
But if you change the parameters, like if you do the microscopy version come a lot closer, then we would have to care. But we don't need to do color when we're doing microscopy because it's fluorescence, which is at a particular color. So we just never did it. But you would have different PSFs there, I think. There was someone.
For the compressive light field microscopy of the 3D neural activity recording, have you guys considered scaling to the human brain neural activity recording, or is the microscopy too stochastic or not linear for scaling to the
There's no reason why not. More like it doesn't work that great yet, so like let's not open up humans for it yet. So also our collaborators are nice people. So our collaborator Khalid Desnik, he's a real neuroscientist. So like we're developing these technologies for him to actually use in practice in neuroscience, and he's studying like cortex, which is near the surface, and like a mouse brain is like small enough that they have a chance to understand things in a way they can't in humans.
For that mouse brain, do you have to use a window chamber?
Yeah, and you have to and it's optogenetics, which also you can't do in humans. Yeah.
Could you say maybe a couple of words about hyperspectral? I think you had one of the other.
Yeah, the hyperspectral version is Christina. She just started her own group at Cornell. She did this all on her own. I just watched. That's what I do now. Watch what other people are doing. Write some slides. Okay, so it's basically just this like erasures idea, but now you have like a grid of erasures that are like. So Christina met this guy at a conference from Viavi Solutions, and they make the color filter arrays to go over sensors. So like your normal color camera has a RGBG Bayer filter, so you can make a hyperspectral camera simply by having an 8x8 grid of different spectral channels. So like each pixel has a different spectral channel, and there's 8x8, so we call this a superpixel, the whole thing. There's 64 in this particular one. And the idea is that so what they were doing was like just give up spatial resolution and call this one pixel, and then you get 64 color channels for that one pixel. But then you lost your resolution by a factor of 64, well, 8 in each dimension. And so Christina's idea was that if you just put this onto the sensor of the diffuser cam, then the multiplexing behavior of the diffuser means that you can just solve this like it was a 3D XY lambda, exact same problem as our 3D diffuser cam, but now it's XY lambda, and you have like and you have like these erasures, like a different erasures pattern. And but then she could solve this to get hyperspectral. And Nirja, newer student in my group, had like extended this to microscopy, and we did all of this work to do an end-to-end design of what's the best. So this like spectral filter, it was just linear 64 channels across the visible. But for microscopy, everyone wants to look at particular fluorophores. There's like, we just picked the 10 most popular fluorophores, or there's like these lanthanide beads that everyone's looking at now that have a particular spectral profile. And so like we designed this, the optimal 3x3 grid. Okay, so 64 is a humongous loss of light. You're killing 64 of the light at each color. So for fluorescence microscopy, it's too much loss. But also they only need to distinguish you between, say, like 10 things usually, or less than 10 things. So we wanted to make like a 3x3 grid that will give us massive improvement in light throughput, and then we'll design the spectral filters to be like ideal for distinguishing these different fluorophores. And this Viavi company that makes this filter said they can make anything, which they can, but then they wanted like $60,000 to actually make it. So we never actually made it. But if you did, then you would be able to do a lot better in the microscopy world. So I think that's actually the benefit of like filters are bad for hyperspectral because they block a lot of the light. But if you can design the filters perfectly and you can choose your filters to be not linearly spaced, I think that's a big benefit over some of the other lensless hyperspectral things where you're kind of just smearing the colors across space, because now you can sort of like pick and choose which channels you want to have be visible. So I think it could have some interesting applications, but we're maybe not there yet. Here's just another example captured image. And you can see like there's lots of artifacts here, but 64 color channels is enough to get whatever these different fluorophore spectras are. Yeah, that's all I had on here.
Okay, if there are no more questions, let's thank our speaker one more time.